Good morning, everyone. Thank you for coming, for those on site, but obviously thank you for those also connected online. Thank you for being here with us at the fastest final event. If you already don't know by now, which fastest means is fast track hybrid system for fast track hybrid platform for battery systems. That's the acronym of our project. Today we will go briefly around our best results in the project, but we are lucky because we are not only the project partners speaking today, but we have with us together our project cluster partners speaking on behalf of their projects, and thank you also for that. Finally, we will have a panel discussion, so we truly invite you all to be with us all around this journey today. And obviously, if you cannot be all the time with us, just for you to know that this session is being recorded and will be uploaded onto the YouTube channel of the project. I haven't introduced myself. My name is Mariana Fernandez. I'm the administrative coordinator of this project, but the technical expert. And the real expert is the project coordinator, which I will introduce now, and he will be giving a few words briefly about the project scope and main goals. He's Bruno Rodriguez, the project coordinator, and he's also project manager at Avesta. So Bruno, a pleasure to have you on board. The floor is yours.
Thank you, Mariana, for your words, and once again, thank you all to the ones online and for the presence here in the room with us. I will try to keep you awake during the morning. This is always a task in these presentations that starts early, but I think the topic will be engaging, and I think the results that you will see, it will also show that this is an interesting topic for you to follow. Now, to give you a quick overview of what is fastest and what was during these last 36 months, because we are 2 weeks away of closing. This is really our last mile. The fastest project aimed to develop the hybrid testing platform that it's focused on the multi-scale and multi-physics and virtual and physics testing. And for this to be true, we came together in a consortium with some of the best expertise in Europe that we can consider, from RTOs to manufacturers to academia, and even with a partner from outside Europe in UK, that it was also great. We have 12 partners in 7 countries, and we had a total budget of around 4.8 million euros to develop this solution. Now a quick overview, and then you will understand by the presentations of my colleagues during the morning. These were our main objectives to achieve, that it was to reduce 20% less operating time on the digital side of the platform, to achieve a 40% ratio in safety, reliability, and perform visualization, to have 3 digital twin demonstrators that will cover aeronautics, automotive, and stationary, and in the part of the simulation to achieve a 50 millisecond faster computational time. But now, and to keep the things running, I will pass the floor to my colleague from Fraunhofer Institute, Philip Brendel, that will present you how design of experiments reshape battery development. Philip.
Yeah, hello everyone. Thank you, Bruno. My name is Philipp Brendel from Fraunhofer in Erlangen, Germany, and we were at Fraunhofer leading the work package on design of experiments, boundary conditions, and methodologies. And in that context, I have the pleasure to give you a little bit of an insight into how design of experiments reshapes battery development and what we did in Fastest to contribute to that goal. First of all, a little bit of a primer on design of experiments and why we even need it in battery testing. So first of all, It's safe to say that battery systems are highly nonlinear and strongly coupled. That means when you do battery testing, you always have to consider various effects, electrochemical, thermal, and mechanical, and they all interact simultaneously. So it's important to have a good design of experiments to come up with a robust conclusion, especially when aging is considered, for example. Yeah, that means testing in general must balance a lot of things such as safety, performance, and parameterization. So you cannot always explore all the critical operation limits. Model parameterization is an effort on its own, and you don't want to have these repetitive and redundant testing campaigns to do that. So yeah, the virtualization potential that we explored in fastest is specifically interesting for that reason. And the question on the right is basically the underlying question for this work package and DOE in fastest. Can we use model-based DOE to improve these things and to select test points more intelligently and identify the key parameters and the points of interest before doing redundant physical tests? So this is a summary of what fastest delivered in all of that. So before, DOE is not a new concept, but a lot of DOE methods are very basic, like they are often called screening methods, and from those you get a rough insight into a battery cell, but you cannot really guarantee any kind of robustness or information gain. What we developed in fastest was a toolbox based on Fisher information matrices, and that led us to the point where we can do a Fisher information matrix based optimal experimental design with a focus on parameterization. Another point, classical model-based DOE approaches are very computationally expensive. So because you have to run models a lot of times for DOE, and in that context we investigated AI-based methods that help in bringing these costs down. So what we essentially did was having systems that have a fast inference basically of these Fisher information matrices, which allows us to scale DOE algorithms and allow real-time integration. Finally, or not finally, but the third point here, these repetitive testing campaigns, they are main bottlenecks because you do the tests over and over. For that purpose, we provided a model-based DOE workflow that smartly combines physical and virtual testing, and that essentially quantifies the information that you get from a certain test before you physically execute it. So this helps with only conducting meaningful experiments first and foremost. Yeah, and then finally, a lot of DOE methods, they are tested and invented and applied, but not really integrated in testing workflows. So this was another crucial point where we in fastest integrated these things directly into the fastest platform and showed that this can work in this environment by seamlessly coupling these aspects. I want to focus on these 2 points here a bit more to give you a little bit of an example what this can look like. So what you can see on the left is some example of DOE where we run the single particle model a lot of times. When you have a lot of designs and you need to have a lot of parameters, then this can accumulate quite a lot. You can see here an estimation of 28 days for a specific example that we used in a paper. These AI-based methods that I was talking about, we looked, for example, at physics-informed neural networks. One of them is depicted here. I'm not going to go into too much detail on how these work, but the main point is with these things, because of the fast inference of machine learning, it's possible to bring these costs very much down. So you can see here another example from the similar paper that we submitted. So it's only available as a preprint as of now. But with these networks, you can really cut down these costs and scale DOE approaches for quite a bit. A second point, I mentioned these repetitive and redundant testing campaigns. What does this mean in practice? So for example, when you consider battery aging, one specific test that you often do is a so-called all-CV test. This is done to understand the open circuit potentials of the electrodes better. And what you want to have in this test is a broad or a wide coverage in terms of the voltage limit. So you can see here an example where we replicated a physical test, and denoted by this cross, you can see that the test was not actually going to the lower SOC ranges of the battery, so it stopped too early. And this leads to missing information, and this leads to models not being parameterized correctly, and this is bad because you have to do the aging tests all over, essentially, or cannot really trust results. And this Fisher information matrix that I mentioned, we can now use this and try to improve this and have a quantification of how this improves. So for example, here we looked at these Fisher information matrices, added different kind of current pulses at the end of this OCV test, and the algorithm basically told us we have found some configuration with some pulses that gives a higher information density. More precisely, you can see here there were a few pulses added towards the end in the bottom row. I'm not sure if this is visible, but there you can see these additional pulses, and this leads to some more information towards the lower end of the voltage range. And yeah, you can see that we were quite happy with that. Going on, a little bit of a summary how the partners contributed to these achievements. First of all, we needed to specify the DOE, the boundary conditions. So we had a lot of partners. I'm not mentioning every one of them, where we initially had to find a path for DOE and to understand where can we really reduce costs and times, which are these tests that are really interesting to focus on. Second, we developed this toolbox considering these FIM-based methods, also considering these physics-informed neural networks to bring down these costs. Then another step was the connection to the models. So we will hear also from my colleague Johannes a bit more about these, but we also had to align these work packages such that everything integrates nicely with each other. And finally, last but definitely not least, the integration into the final platform. So this was, of course, the last stretch of this to not only make sure that this works in practice in a safe environment, but also in the actual testing platform. And I'm happy that we achieved that as well. So short, who can benefit from that? Of course, battery manufacturers in these things in terms of time and cost reduction. These DOE workflows, they can really help. We showed that it's possible to scale up these approaches and to improve things. Battery testing facilities as well, because this now gives a path to really combine these tests physically and virtually on the fly and not have these redundant testing campaigns. And then, of course, also the research community, specifically in this area of physics-informed neural networks, where we also did some dissemination in the form of peer-reviewed publications, and I think that's also a nice outcome of this whole topic. Summing up, if you want to keep 3 key takeaways. So first, this intelligent model-based DOE framework, what was the focal point, specifically focused on these 2 concepts, physics-informed neural networks, but also this more general mathematically rooted concept of Fisher information matrices. I didn't mention that before, I'm realizing right now, but what they basically do is give you a sense of sensitivity of the parameters with respect to the model outputs. So this is what the Fisher information matrix is. And yeah, the smart coupling of this virtual and physical testing, this is essentially can lead to results like this. This is of course not the end of the story, and there are much more directions to explore and much more tests that this can be applied to. But yeah, I think this is a pretty nice proof of concept. And finally, also this research direction that we investigated specifically with physics-informed neural networks and their applicability to design of experiments. Yeah, and with that, I would thank you for your attention and hand over to my colleague Johannes from Mondragon.
Before moving ahead, I didn't mention, but obviously if you have any question after each presentation, you can post to the people speaking, both the people on site and online. For the online people, you have this Q&A tab where you can post the questions. And anyway, if it doesn't work for you, you can also put it on the chat, and we will try to answer those. We will, even if it's later and the speaker are already not on stage, but we will keep those and ask them later. And no further delay, I will introduce Johannes Berasategui. He's responsible for the advanced aging performance modeling and a researcher at Mondragon University. Johannes.
Thank you very much, Mariana. Okay, I'm Johannes Berasategui from Mondragon University. Okay, and I will focus now in the main results that we have obtained for package 3 regarding the modeling task. I will not go very deep into technical details. I will go for the overall overview, but I have some technical aspects to mention just to understand the main objective of these tasks. Okay, so what we want is fast and reliable models, tools that enable us to substitute experimental characterization tests. Okay, for that we have different approaches. In one side we have the multi-scale, multi-physics modeling, and also we have the data-driven models. So the main schema of the tasks that we have working on during these last 3 years is more or less this one. It's a summary. I may be missing some details, but we start for defining cell specification. In this particular case, we work with 2 different cells, different chemistries, and different electrolyte formats, both cells in pouch sizes. Okay, so from this cell specification, we take the input parameters for the materials, the geometries, the thicknesses, and so on, and we define the multi-scale, multi-physics models. We start from a very small scale, like trying to understand what's going on in a particle scale, in which you have the materials, the electrochemistry, it's important in this scale, and we have the whole cell that it's important for thermal heat generation and heat diffusion. And then we move from this cell level to the module and to the pack scales. In the mechanical aspects, we also have analyzed the mechanical behavior of tabs joining and how they behave in different conditions. So these multi-scale, multi-physics models are performed first at full order, high fidelity models, and we go then for an order reduction in order to improve the simulation time. As I mentioned earlier, our objective is to have accurate models but fast. So as a final result, we have validated that we have a good accuracy for both cells, both chemistries, with errors below 1% in both cells. Okay, so this comparison has been done at cell level. We have also reached a good accuracy for pack level. So here we show some representative results for the cell and the pack, comparing the voltage measured experimentally and predicted by simulation. And also we have demonstrated that these models are fast enough. We are having a simulation time below 50 milliseconds per time step. So this is one of the second objectives. Obviously, the models at cell level are faster than the ones at pack level because we have auxiliary elements, we have the cooling technology, we have more constructive elements at module and pack level, but in all cases we are achieving this objective. In parallel, we have also the data-driven models that they are fed by the multi-scale modeling and also with testing results. And obviously we use some of the testing to do the validation of the models. So overall, this is the main schematic overview of the work package. And now we'll move on to more generic results that we have obtained and the conclusions that we can obtain from this one. So the main objective was to develop fast and reliable models considering multi-scale and multi-physics, covering from cell, module, and pack level. So for that, we should take into account, as I mentioned, electrochemistry behavior, thermal behavior, and mechanical behavior. So it's all put together in same models. Okay, we have implemented different approaches like physics-based but also data-driven modeling, and we have seen the comparison between them. In order to have a good accuracy, probably we need to go to physics-based, but data-driven modeling even can reach faster simulation times. For faster simulation times, we move from high fidelity models, full order, to reduced order models, and we achieve from that the objective of simulation times. And these simulation tools that have been developed from cell definition has been validated with performance results, thermal results, and also some aging results. So we have demonstrated also that this approach is valid for different chemistries. LFP and NMC cells have been analyzed with solid electrolyte and liquid electrolyte. Well, let's say semi-solid electrolyte. You know that semi-solid electrolyte cells are the first step towards the full solid-state batteries, in which a huge step forward is expected in order to have a higher capacity, better security, and also faster charging time. So this is the first step, and we demonstrate that this approach is valid for semi-solid prototype electrolytes, and we expect to be also valid for future full solid-state cells. And also, one of the latest, but not least, important thing is the interoperability of these models. I mean, the models work successfully, they are accurate, they are fast, but they should be transferred to other work package in order to be applied in the final platform. So for that, we use standard formats in the FMU versions, and for that, we can achieve other downstream application, like Philip talked about the design of experiments, and also the VM development has been done with this model. Okay. So this was needed because industry needs higher capacity of virtualization of battery, virtual prototyping of battery, because we have an increasing battery complexity of battery systems. I would say that the models right now are getting very accurate, but we need to make some efforts to make them as fast as possible. Okay, and this can give us some advantage in time and cost and scalability behavior. So, well, I will also want to thank all of the partners involved in this work package. Okay, we were like, Mondragon was the technical leader. I want to mention here Laura's work. She's not here, but she has been working so hard during these last 3 years. I'm here presenting the main results, but I think her effort should be also addressed in this meeting. So, well, we were technical leader. We have 9 partners participating in these work packages. Some more focused on the physics-based modeling, other ones in the data-driven models. Some supporting with input parameters, testing results, and so on. So I think that we have faced several difficulties, but we can say now that the main results, the main objectives has been fulfilled. So I want to thank you all for the hard work and for the not only the effort has been great, but also the results and the quality of the work has been great. So thank you all. Okay, and also we, as I mentioned previously, we have some integration with other work packages, like design experiments in work package 2, but in work package 6, like BMS optimization, and also the standardized interface and formats in FAU to the final platform. Okay, and well, what's this for? Well, we think that these models can work in a very open perspective, like manufacturers to better understanding the internal mechanisms of their battery systems, like OEMs on system integration to faster prototyping, virtual prototyping, and to have a better design of these systems, but also for research aspects, as Philippe has said. I think that this model gives us a physics-based vision of the main mechanisms in very different aspects of mechanical, thermal, and electrochemistry behavior. So overall, I would like to enhance the knowledge transfer between different disciplines. Is not easy because each mechanisms or let's say approaches use a different environment, but we were able to put together this all knowledge by linking different disciplines. And the contribution to interoperability, that it was the main objective of this project, but it was also one of the trickiest points at the end. Okay, so as a summary, well, main ideas, we were able to capture the battery system behavior holistically, considering different scales, considering also different mechanisms. Okay, we have used different approaches. Maybe one more focus on the accuracy, other ones more focus on the simulation times. But in a combination, I think we have achieved a very high options. We have the model order reduction as a key element to reduce real simulation time and reach larger scale simulation, especially for pack scale. And always we try to feed our models with very less experimental tests. This was one of the objectives that we have initially, but experimental validation, especially at higher scales, will remain critical in order to have a good validation and a good model credibility. Okay, so this is more or less the overview of work package 3 and the modeling task that we had in fastest. So maybe if there is any question, or maybe we can at the end.
I believe there is no question.
No question? Okay.
At least by now, there is no question. Thank you very much, Johannes, and thank you for that big applause. Right now, we will move to two speakers. On the one hand, we have Vijay Nagulapati. He is battery safety expert within Roster and obviously within Fastest as well. And on the other hand, we have Sina Sajadpur. He's machine learning expert at Avesta. So we will start with Vijay. Vijay, thank you very much for coming. The floor is yours.
Thank you. Hello everyone, good morning. Sina, you can come join me here. Yeah. So this is work package 4, presentation for work package 4, safety by design, which was like co-executed by me and Sina as a team from Avesta, Sina from Avesta. So topic as a snapshot, the main objective of this work package 4 was to provide or create a multi-domain tool chain which for virtual testing and analyzing and evaluating the battery safety and reliability aspects. So this work package had scaling from cell to model to pack or system level and dealing with 2 different chemistries, the Gen 3B and Gen 4, and for 3 different use cases, automotive, stationary, and off-road. So here what we did was we treated the safety, aging, and reliability as a coupled concern and not as separate individual identities. Virtual models were developed which complemented the physical testing through traceable validation evidences, and the digital and hybrid testing compatibility was ensured. So if you see here the schematic of the work package 4 and the various tasks associated with it, where we have the cell module and pack level campaigns, the framework of the modeling, and as such, so the validation framework as well. In Fastest, what Fastest has delivered is a robust architecture for the multi-domain toolchain with the inputs and outputs. Then high fidelity model like data-driven models for AI estimations to convert battery inputs into safety and reliability indicators. There was this risk logic that was implemented by using FMEA and HARA standards and standard alignments and interoperable interfaces. The validation and verification strategy was also implemented where the DT compliant validation framework was established. KPI logic and experimental evidence and validation maturity were all captured in a transparent way. So I think this is where you come in, Sina?
Yes. Yeah, thank you. Oh, thank you for introducing the part. So I just go in an abstract level, but if you have any question, deeper level, it's better we can discuss here. So the main idea was that we can consider the battery cells, different types of battery cells in different abuse conditions. That what will be happen to the battery cells if they exposed in abnormal cases or abuse cases. Well, we divided the model into two parts, two abuse cases. The first abuse case was overcharge and over-discharging. What will be happen to the battery cells and how the battery cells will behave in these abuse cases. And the next part was what will be happen if the battery is exposed in abnormal temperatures. What we considered here was only extreme cold conditions. But we tried to make a platform that can be evolved during the time. So making something robust or something general that can be developed in many cases. But in the overall view, we just considered that we want to develop 4 models for 2 different battery cell types, which were Gen 3 and Gen 4 batteries, and develop different models for each of these cells for overcharge, over-discharge conditions and extreme cold temperature conditions. What we wanted to expect from the model that how the cell will behave was, let's see that what will be happen to the battery cells if we overcharge or over-discharge them, what will be the maximum voltage in overcharge case, and for over-discharge case, the minimum voltage that it can face. Also, we wanted to measure other characteristics of the cells, like predicting the capacity fade, increase in internal resistance, and the temperatures of the temperature of the cells. So the main idea is we develop something that can prevent the cases that the battery can be, let's say, exploded or be dead. So the main idea is a preventive model, and these data will be sent to a decision maker to decide that in which state the battery cells it is, and it can be used in like I said, a decision maker. What we tried to develop was a data-driven model. So based on this data-driven model, we tried to test the many battery cells. We were a lack of batteries because we had lots of tests. One test, if I come back here, one test we had to run for overcharge. we couldn't use the same cell for over discharge because that battery cell is not 100% SOH or healthy mode. And another battery cell for extreme cold temperatures. And also, for example, we wanted to, for overcharge or over discharge, we had different levels of SOC. For example, we wanted to check the battery cell, how it behaves if it overcharged to 110%. We couldn't use the same battery cell when we wanted to check the cell capacity when we overcharge it to 120%. So this was a limitation on developing this model. We had to run many tests, and we don't have enough cells and time. But the main idea was to develop to set a platform that can be developed during the time, even for many other cases, if we want to run a test for extreme hot conditions. So the data-driven model was the safest idea to develop this. Well, many of you know about how the data-driven models and machine learning models are working. So we have a train phase and a test phase, which the test phase is actually our predicting model. What we expected from these models, we wanted to reach the highest accuracy for the models. So for each of these specifications, for example, internal resistance, how it will change, or the capacity fade, or the temperature and voltage, what we can expect from the battery cells if they are exposed, for example, in overcharge case. We developed different models, so we separate them all to gain the highest level of accuracy. So in the train phase, we run some we expose batteries to overcharge, but on the other side, we also had a 0% to 100% of specifications on 0% to 100%, and we just monitored, or we recorded for example, I just give an example, the voltage of the battery when we reach to 100% or 110%, and we trained the model, and on the other side we just inject the voltage curve, the voltage profile of the cell, and what we expect from the model, it should spit out what are the voltage of the battery cell if it is reached to 110% or 120%, what will be the temperature, what will be the capacity fade after exposing to 120%, and what will be the internal resistance change. Please, if there are any questions, interrupt me. This is the results that we could gain from the models. The first two here you see is the error of the model for estimating the voltage if we overcharge the battery cell. For example, here is 105%, 110, 115, and 120%. One thing we have to mention that we all the battery cells that were being tested, they all had 100% SOH. So for sure, if we expose the battery cell with SOH of 80% or 70% or 90%, for sure we won't have these errors, because the errors can be much bigger than this, because the models are trained based on batteries that their SOH is 100% their state of health is 100%. But what we tried to develop was a platform, something that can be developed during the time. So all we need to make our model robust is that we run a test for some battery cell with different SOHs. And we inject the data in the training phase, and we expect more accurate results. That's for the voltage. This is for the temperature. For the voltage, we saw that, yeah, this as the battery cells increases the SOC level, not necessarily we are far from estimation. So our estimation was, we couldn't say that, yeah, this is increasing. Actually, this is showing that at the 120%, we can estimate the voltage of the battery with much more confidence when we want to overcharge it to 110%. The reason, I don't know. And for the temperatures, but we see, yeah, this is different cases from the voltage. With 110%, we have more accurate estimation than we go to 120%. So estimating the temperature of the cells, as the battery is going higher in SOC, we have less confidence. And there are two other results that I'm just showing here. It was for the capacity and internal resistance. For the capacity, we almost had very close to zero error. Our accuracy was so high. But after we investigated this, we found that the test that we run was not, we cannot say that they were correct. When we overcharge a battery cell to 120%, it is not necessary that it shows that the capacity is faded in the first few cycles. Maybe you have to go more than 100 cycles and you see a drop. Actually, this is what it happened. But the data that we used, this is exactly, we exposed the battery to 120%, and after that we discharge it, and we check the capacity of the cell for the first 2 cycles. So we couldn't see that it could be dropped or changed a lot. But for the internal resistance, it was huge, the error. And we could measure it, and the result was obvious. But like the temperature, as the SOC increases, for example, from 105, we have more confidence than 120%. So as the SOC is increasing, our confidence of prediction is getting maybe worse. So if any questions, please ask. In other case, I will leave the floor to Vijay.
Yeah, before that I have one question. If you
I think online they won't hear you. You have to take the microphone. Sorry.
I just had a question regarding the training data set. So we trained this model based on the safe zone data, or you use some abuse condition data as well in the training?
For sure we need to run the train set. Is that we have to see how the battery reacts in unsafe zones. Mm-hmm. So if we don't run test to 120%, and we don't know what will be the temperature, what will be the voltage, in that case, thank you, Maria. In that case, we don't know how to estimate, how to predict.
Okay. So because that was interesting, where at 110% the error was higher, but at 120% it was like more closer to, like the error was lesser, right? So I was wondering what kind of data we use in the training. So yeah.
No, for sure we had to run this. But what during the tests we there are many test scenarios. But we, like I said, we had many tests we had to run, and we didn't have enough cells to test them. For example, for the overcharge, we used a very low C rate because we were not confident that if we reach to 120% of the SOH, first of all, if we use a high C rate, for sure the voltage, the load voltage is so high, so the explosion of the cell can be higher.
Higher. Risk increase.
So but maybe in some real cases, you run a battery cell with a high C rate. If you use these models, maybe you don't receive that, maybe it cannot even estimate what will happen to 120% because it was tested on low C rates. For higher C rates, when we gather more data, more input data as a training test, we will have more confidence. So our model will be much more robust.
Yeah, agree. At this state of campaigns that we have run for the testing, this is where we are, but more testing, more data, more training, and we will have more accurate results. Yeah.
Exactly.
Yeah, got it. Thank you. Thank you, Sina.
Yeah.
So moving on. During this work package 4, why was this needed? Like, what was the need for this? So there are certain pain points in testing of batteries, developing of new chemistries, like the testings are slow and costly. Electrical thermal aging and control behaviors interact across scales, like from cell to module to system levels. Evidence at a prototype level is usually incomplete and doesn't have enough information that's needed for the design teams. So what we did was, in Work Package 4, we developed a modular multi-domain toolchain for the reliability assessment, virtual safety and reliability assessment, and as Sina has just explained, AI-assisted estimators to predict voltage, temperature, internal resistance as such for the batteries or the new chemistries that we're developing, and standard adhered logic, like risk logics, using FMEA and HARA techniques for traceable risk reasoning, and a robust validation and verification framework classifying the validation approaches and the maturity levels of each validation. How partners made it work? I would say it was a lot of input from the whole consortium, where we had inputs from other work package 3, work package 5 for the digital twin, and 6, work package 6. And within the work package 4, Ruster was in charge of the architecture and safety by design logic. ABE and ABEMK were defined the baseline for the batteries, developed the estimators, and implemented the tool chain. Universities like Ljubljana, INEGI, University of Surrey, Ikerlan, they were in charge. They contributed in developing the aging models and the interfaces, DT input-output criteria, life cycle, and reliability support. Flanders Make and VTT were primarily tasked with the experimental campaign, where they had run some tests, experimental validation perspective, provided electrical and thermal procedures, evidence boundaries and stuff. So what we did here holds for the stakeholders. Basically, this hybrid testing platform, multi-domain toolchain, what it does is it gives a structured pack level evidence, failure path interpretations, and operating envelope insights for the manufacturers, OEMs. For the R&D teams, they provide reusable safety and reliability models which allow faster screening of the designs options before expensive physical tests. For the test laboratories, better prioritizing the campaigns based on the severity or the value of the abuse condition, like which test needs to be done at a higher repetition and stuff like that. And for the digital platforms, we have like FMI, FMU based and DT ready outputs that can be reused in the virtual benches and hybrid testing workflows. Key takeaways are the toolchain architecture, which was established, multi-domain toolchain architecture, then the combined physics-based AI-driven, data-driven logic for safety and reliability assessment. System-level integration was demonstrated from cell to module to pack logic, and the risk logic was implemented using FMEA techniques. Then the validation evidence, where specific KPIs were established for the validations, and limitations and the boundaries were captured. Limitation boundaries were captured transparently. And I think that pretty much sums up what we did in Work Package 4. Thank you. Any questions? Thank you.
Seems like everything was pretty clear. Thank you very much. Right now we have also two speakers on stage. I will invite you to please join us. In the first place, we have Marcos Rodriguez from INEGI. He's AI and Data Research Coordinator, and Maria Grazia from Comau. She is our digital twin integration expert. So the floor is yours, guys.
Thank you so much. Good morning, everyone. So moving on to present the main outcomes and results from Work Package 5, which was more focused on the digital twin. So we started our work focusing on the ontology for battery testing. So establishing a vocabulary to formalize concepts and within the domain of the battery testing, battery cells, modules, tests, procedures. This was a way to standardize the battery testing knowledge, and was also the first step to structure data, to model data, and organize this complex domain knowledge into classes, properties, relationships, and make things work and fit all together in terms of data modeling. This was also this first step also resulted in a first publication towards developing an ontology for a digital twin in battery testing. And then with this we were able to formalize, okay, let's structure a methodology for a digital twin based product testing in industrial settings. We defined the key steps, for instance, the goals mapping, what is a digital twin for, what's the main objective, the categorization of the digital twin, what type of digital twin are we talking about, is it a system digital twin, a full process digital twin, just a product? There are several ways to approach the problem. Defining the core elements, the core components of the digital twin that can cover the model management, the test orchestration, data management for simulations, data handling, etc., and also to structure a modular and scalable architecture, which in this case based on microservices and deployed on a cloud platform to enable security, to be able to scale and to provide interoperability. This work, as focused on the methodology part, was also part of a publication targeting digital twin-based product testing in industrial applications. And now I will pass the word to Maria.
Thank you. So, the digital twin is a cloud-based software platform built on a microservice architecture. The aim of this digital twin is the orchestration of test requests sent by LIMS and the determination of the procedure, the test procedure. Then the management of simulation models with the component realized by INEGI, the models exchange interface, the collection of test results data with the microservice called data collector, and then the visualization of these test results on the dashboard. So with this fastest project, we realized a hybrid testing platform, so a powerful tool that enables virtual testing and the comparison with these results with the results of physical tests. This digital twin, this platform, is not tailored only for one use case, but for automotive, stationary, and off-road use case. And throughout this project, there was the transition of the digital twin from a theoretical framework to an integrated prototype validated in the industrial environments. So this digital twin is not only a powerful tool, but it's also useful for because it's time-saving. Since there is a combination of physics-based and data-driven simulation, reducing the need of physical tests. There are also cost reductions, so there is the minimization of resource consumption for the physical tests. And also there is also the robustest data history. So this platform accumulates with the data collector historical testing data over time, continuously capturing and storing operational inputs. So for the realization of the digital twin, there is a contribution of all partners for the fastest project, in particular partners of work package 3 and 4. And we Comau realized the digital twin, which enables to virtually execute the test. And each component of the digital twin, so the data collector, the model management, test request handler, and models exchange interface, facilitates a seamless data exchange and storage. And then it was important the contribution of the INEGI, which realizes the models exchange interface, which allows secure sharing of the FMU files. And we integrated their component into our digital twin. And then also it was important the contribution of FEV with the LIMS integration, which was the test orchestrator and interconnects all the platforms, so LIMS, our digital twin, physical test bench, virtual test bench, and the DOE algorithm. This digital twin, so this platform has a value for stakeholders because it enables partners to have accurate virtual tests. And this leads not only to catch performance anomalies long before physical prototyping, but also it allows to minimize the dependency on costly and time-consuming physical test bench cycles. And that's it for the digital twin.
Thank you very much, guys. Any question? Very interesting presentation. Probably if there are questions, as I was mentioning before, we will ask later to the speakers if there are any questions on the chat. So thank you very much. We will leave the floor now to Suhen Liu. He's our expert on the platform you will see on the screen. He's also doctoral engineer at FEBIO. And he will show really interesting results. So, Suhen, the floor is yours.
Thank you very much, Mariana, for your kind introduction. I'm Suhen Liu from FEVIO, GmbH. And so at FEVIO, we are providing the engineering services for software and system-oriented solutions. And as we did for fastest project, so we have heard a lot today about the challenges for the battery testing. Just as a summary here, we are facing a lot of time pressure, especially in Europe, for the battery pack validation. Today it takes up to 1 year. And we have limited capabilities of the chambers and so on, especially for the abuse test. And limitations of the data storage and sharing is also a topic nowadays when we are facing the battery passport regulation, and the physical testing is avoidable, as our DOE colleague Philip has introduced us by virtualizing the battery testing. I'm just right now putting the pieces together, as you can notice. which has been done in the fastest by the modeling and digital twin management colleagues, and by applying the smart design of experiment and testing scheduling. However, the virtual testing is not sufficient because we have limitations of the modeling. We have experience today, right? For the working back 3 and 4, models are good, but they have their own limitations. And also the regulation still requires us the physical validation. That means we cannot solely relying on the virtual testing and physical testing. Instead, in working package 6, we build a central orchestration layer that connects all the pieces we have heard today from working package 2 to 5, and connecting the physical test benches, the virtual test benches, the scheduling, the DOE, the DT, and through a single cloud-based platform, which is called LIMS. We will have a closer look at the LIMS today. Before we have LIMS, I believe everyone here has experienced projects that is with focus of the virtual testing or physical testing or hardware in the loop testing. However, there's no shared control layer that combines all these kind of testing together. That's the reason we have the LIMS, Laboratory Inventory Management System, as the orchestration layer, and manage the all kinds of testing types and requests together in one platform. And earlier, without our fastest platform, the typical battery testing process begins with the customer going to the testing facility and say, "Hi, I'm the customer, I'm the OEM. I want to do this and that test with my battery pack." This is normally communicated by email or a document description, and that requires the manual analysis with a battery expert and break down this test request into test orders. Now we have the LIMS user interface. We have standardized this process, right? Namely, requesting the user to provide us the input that we require to execute the test request in a standard format. And the manual scheduling, so earlier that breakdown has been done, and the manual scheduling will be also done by a battery test expert, and arrange the tests, distribute them into the chambers, and arrange them timely. Right now, this task has been replaced by the intelligent scheduler, optimizing the bench allocation across the physical and virtual resources, and minimizing the bench idle time. The simulations were rebuilt for every campaign. Earlier, we have the simulations, and for each test, we need to rebuild the test, the model built by either Simulink or whichever other language. The rebuild normally combines with the debugging process and so on and so forth. Right now, in this project, we all share the same common sense that we should provide our model in the FMU format, functional mockup unit, such that the debugging process is more flexible and the sharing is more standardized. And with the description of the interface, we can build our simulation in a much more flexible way. And this has been simulated on a cloud-based core simulation engine running the FMI 3.0 standard-based FMU's pipeline. And this pipeline can run the simulations concurrently and auto-scaled. And the last point was the real-time bridge communication among the test benches and so on. The earlier systems I would prefer to use the word closed. So within the system, everything communicated in a real-time manner, which is perfect. However, our system is quite open, so we provide the standard communication interface in the MQTT format, and that makes it flexible to connect to each and every partner labs. We will see the result layer, including the Flanders, Make, Flash Battery, and Eclan in our case. Also, the communication among the components of the LIMS has also been realized in the same way. That means we have a standard message structure within the fastest project for information exchange, and which makes our system robust, but remain the openness of the system as well. How we achieved it, these are the partners who has contributed to this platform. Of course, it's everyone. So I have tried to avoid repeat the logos on these pictures. Otherwise, it will be very overwhelming. But here, the process begins with the LIMS UI. The user requests the test by defining the due date, the UUT, the use case, the standard that the customer want to use to test the battery, and the test name. And then DT received our request and decide whether the test can be virtualized by checking the available model and test procedure. I'm sorry, I know I'm repeating what the colleagues has already said, but this is the pipeline, right? I really hope that, I really appreciate that you can remember this, because later when we look at our result, it will be important to understand the process. Provide FMU and test procedure to the LIMS for the virtual testing. So once the DT decide it should be virtual, it provides us the files that we need to simulate. And the DOE calculate the optimized parameter from and decide whether the test should be virtual based on the optimality that introduced by Philip already. Decided the physical test bench, if it is decided to be a physical test eventually, we will decide which physical test bench should be used for this testing based on the test bench capabilities. And eventually this test request will be complete and sent back to LIMS, and then we will check this test schedule and distribute the test request to the corresponding test bench at the time that we scheduled it should be carried out or executed. So the virtual test bench, so if it is a virtual test, of course, so the green ones are the virtual test track. It will be distributed to our virtual test bench, core simulation platform, as you can understand. And if it is a physical test, you can see the 3 tracks in this fastest platform. We have the physical test bench from Flanders MIG, and we have the one from Flash Battery and Iklan. Each of them is targeted for one use case, and different battery levels like cells, modules, and packs. Eventually, the test will be executed at the requested time, and then the result will be sent to the DT in real time to be visualized on the dashboard, and eventually this will be the result that we expect for our test request. And of course, each one has a unique ID. Each test request has a unique ID such that we can track. Before jumping into the result, we understand the system, we understand the pipeline of the fastest platform, and the benefit of this platform is for the battery manufacturers and OEMs. Of course, we can accelerate the R&D cycle by virtualizing some of the tests, for example, and we will have fewer physical tests before designing sign off. And the battery testing facilities, especially we have the automated scheduling replacing the manual planning and the managing the physical and virtual test process in one place. We know a lot of testing facilities right now in Europe. They're not only providing the physical testing, they're also providing hardware in the loop and virtual testing in the same place. But when you look at their brochure, for example, they have one team for virtual, one team for physical, and one team for hardware in the loop. There's no centralized place to manage all these testing checks. So the LIMS provide a platform for that, including all kinds of tests and managing them and tracking them. That's the most important, right? So if the customer asks you to have to test for their pack, you want to track all the test orders and make sure that you do successfully satisfy the test request, right? And eventually, for a lot of testing processes, audit trial might be requested, and we provide a full record for that. As to the regulation and policy, the architecture is cloud-based, which is very friendly to the upcoming battery passport requirement. Another point I didn't I haven't written here is that, of course, our platform is one of the first for this kind of hybrid testing, and it should be helpful if the decision makers want to have some kind of the guidelines and standard for the combined physical and virtual testing processes. For the research community, we provide this cloud native architecture. We also publish that, where we are going to publish that. We have a patent that people can read about it. And we have the FMI compatible co-simulation platform based on the commercial software. We have the optimization-based test scheduling based on the Groovy solver, right? We have described all this kind of development in our deliverables already. In the end, this is really something I want everyone to enjoy watching and take home. This is our end-to-end integration workshop, video recorded to demonstrate how actually our platform works, including all the components you have heard today. That was a long workshop, but eventually we could demonstrate what we wanted. So this is the LIMS dashboard. As you can see, the test request and all the details from the history. And on the left-hand side, you can see the physical testing track, and on the right-hand side, you can see the virtual testing track. In this demonstration, we are targeting to run the physical testing and the virtual testing in parallel. And on the left-hand side, you can see we can choose the due date, the UUID, the use case, and the standard. And as you can see, the test request has been sent out, and the DT is running right now. And DT has already decided that it should be a physical test. That means when DOE received this test request, it already knows that DT cannot virtualize this. On the right-hand side, we are requesting a test at the same time. It is for the Gen 3 BCL, automotive, and OCV test. And we submit the request, and as you can see, the DT is running really quickly and complete, and give us the feedback. When we updated the left-hand side for the physical testing, we can see the DOE is already complete, and the test scheduling has been optimizing, and the test has been scheduled. Soon we will see when it is scheduled. It stays firstly in the test request pool. It stays in the pool until the test, the scheduled time point is coming. We will send this test request out, and the test will be executed. As you can see, it has been scheduled like several minutes after we created this test schedule, and it has been sent. It will be sent to the physical test bench. At the same time, if you take a look at the virtual test track, it is running a little bit slower at this stage because the DOE is optimizing the profile. As you can see several presentations before, it tries to provide the optimized profile. And so here now you can see the physical test has been started. So in this test, the physical test, because of the test type, it is targeted for the Flanders make test bench. And right now, behind this video, the test data has been streamed from the physical test bench Flanders make to the cloud of the LIMS. And we will see the result in a second. On the right-hand side, we can see, the test DOE is also complete. That means we have the optimal parameter for this OCV test, and the test has been scheduled as well. Okay, now we see the physical test bench results. So this is the physical test has been already complete, and we see the result on the dashboard of the digital twin. At the same time, the virtual track is still running. It has been scheduled. And we need to wait a second until everything is done. So it normally takes 1 or 2 minutes before we can simulate it because, as I said, our platform is scalable. That means we don't running all the virtual test benches all the time. We bring one of the core simulation software into live when we receive this request that normally take 1 to 2 minutes to load. And that's the reason we wait for another minute before the simulation start. And you can see here the simulation started already, and we are right now receiving the simulation result on the DT side as well. So the simulation has completed, and we see the result on the DT dashboard as well. Just as a disclaimer, we see the result from a demo FMU, not the functional FMU on this dashboard. So that's the reason you see the beautiful sine curves. Yeah, as well, you can see the values on the DT dashboard and check the output of this result actually in the real time, but just due to the limitation of the demonstration, we check the result till the end. And another information is that both physical and virtual tests in this video has been chosen to be 100 milliseconds, 100 seconds, such that we can finish the demonstration in the planned time. But in the reality, the physical test takes hours or days, and the simulation should also take minutes to hours as well. So that's basically it. We have seen the how the fastest platform works as a whole, and yeah, I hope you enjoyed the video. Thank you very much. That's it.
Thank you very much, Suhen. Any question for Suhen? If not, we will move ahead to our last presentation of the morning. In this case, it's a bit different because Pablo Ariño is connected online. He's our exploitation and IPR manager for Fastest, but he's working as a business developer manager at Sustainable Innovations. Pablo, I believe you hear us. Whenever you want, you can take the lead. I will pass the slides for you. Is that okay?
Can you hear me?
Yes, indeed.
I'm listening myself a little bit, but that's fine. Thank you very much, Mariana, for your kind words. And yeah, good morning, everyone. As Mariana introduced, my name is Pablo Ariño. I'm from Sustainable Innovation, and I lead the exploitation and IP management work package within the Fastest project. So my job today is to tell you not just about what we built, that you have already heard about it from the technical teams, from the great technical teams presentation, but what happens next. So how does a 36-month Horizon Europe research project become an industrial product? So that's what we are going to tell you in the next slide. So here, first, a Fastest snapshot. So let me first start with the problem that we aim to solve from the very beginning of the project, because context, of course, matters when we talk about impact. Battery validation today face many different problems, such as the one that has been explained before. For instance, the single battery pack can take up to 6 months to be validated, and therefore physical test, HIL environment simulation tools, and LIMS systems all operate in complete isolation. So there is no coordination layer that exists between them. So the result is a chronic bench underutilization, redundant physical experiments, and data fragmentation that prevents any kind of automated compliance reporting. Therefore, the problem, once the problem is analyzed and identified, the fastest answer is the hybrid testing platform, the one introduced in detail by my colleague before, that has been entitled in Key Exploitable Result number 1. By the end of the project, we've demonstrated up to 41% reduction in R&D time and from 20 to 35% reduction in testing cost. Therefore, we can say that we achieved a Tier 6 validated in an industrial environment. And not only this, but we have also a clear roadmap to the commercial deployment foreseen in 2028. Finally, we're talking about a market that is growing from 103 billion in 2021 to 362 billion in 2030. Therefore, the timing could not be better. If you can go to the next slide, please. Yeah, perfect. Thank you so much. So what Fastest delivered? Fastest, the project itself, delivered 6 different key exploitable results, which are 6 modular, individually valuable tools that are all of them integrated into the hybrid tested platform. The different technical presentation were very detailed and but mainly all of these technical outputs have been embedded into these 6 curves. Curve number 2 brings the intelligent DOE methodology that tells you which experiments to run. Curve number 3 brings the physics-based model at cell, module, and pack level. Curve number 4 brings the data-driven aging projection. Curve number 5 brings the AI-based safety and reliability toolchain. And last but not least, the curve number 6 brings the digital twin layer that ties everything together. So we started the project at TRL 3, and we closed at TRL 6 with a credible plan to reach TRL 9. All of this effort has been made from 10 partners from 6 countries, each contributing to different pieces of outcomes. Why this was needed? Want to be very concrete because the transformation is very significant. So here you can see on the slides how the fragmented variety testing looks like before and before Fastest that were physical and digital tests conducted in isolation, manual scheduling, HIL validation limited to isolated subsystems. The models were sitting in one silo, the test data in another, and the limbs in a third. So this leads to months of testing for a single pack. After Fastest, we achieve a single orchestration layer that integrates all of this. There is a scheduling that automates resources allocation, demonstration for full system validation, the digital twin reuse that eliminates the redundant physical experiments, and of course, full data traceability from raw bench data all the way to compliance evidence. So this is not just an incremental improvement, but a structural shift in how battery validation is done. Next slide, please. Yeah, all the partners have been introduced in a very detailed way previously in all the before presentation, and you should be able to get a clear image and picture about what each of them has performed. So, but you can have this all the different layers that have been contributing from the lead exploiter to industrial adopters, DT platform, of course the use case partners, the industrial adopter, technical partners, and DOE partner. All of them contributing to a well-functioning consortium. Each contributing with their best features and getting something back, of course. The value for stakeholders from the impact perspective. So, of course, for industry, automotive OEMs and tier 1 suppliers get faster time to market and lower testing cost. So this is going to be a very clear competitive advantage. The gigafactories get scalable validation infrastructure. Battery testing laboratories also get a hybrid service model and potential new revenue streams. And industrial manufacturers working on BSS, off-road or aerospace batteries get a real condition validation. From a research point of view, universities and RTO get a validated open platform for modeling and DOE research. The National Lab get a digital twin and HIL infrastructure for next generation of cell development. And startups get access to state-of-the-art validation without massive capital investment that could be needed before the Fastest project. Finally, for policy and ecosystems, we can be quite proud of that the platform directly supports the EU battery regulation, accelerates the EV battery qualification, and is reusable across the European battery value chain through the BAT4EU and in similar initiatives. So here you can see on the slide, I'm not going to be into detail for each of the different layers of the Lean Canvas model, but this is the slide that represents and illustrates the business case on one single page. I want to highlight three things. First, the problem that it's real and urgent, the battery pack validation delays. So the different tool exists, but nobody has connected them until the fastest project. Second, the unique value proposition that we are the only platform that integrates DOE, HIL, digital twin, and LIMS into one real-time decision-driven layer. And third, the unfair advantage that is already in place, but the patent filed by FEB, protecting the scheduling and orchestration logic. Also, by being validated the TRL6, we confirm that the early adopters inside the consortium can move ahead for their TRLs. And finally, the road to market. I want to close the presentation showcasing that the road to market is clear and credible pathway where research becomes industry, right? So we close right now at TRL6, and by the second half of 2026, we expect to move into industrial hardening to begin reaching out external from the consortium early adopters. 2027, we target the first beta commercial deployments with external OEMs and tier 1 customers by offering licensing agreements that could become active. 2028 we'll say if we can say that we can target the full commercial scale reaching TRL 9 with the Gigafactory deployment and revenue generation across the different exploitation leaders of the consortium. So this plan is defined with partners, milestone, and confirmed investment commitments. So that can be like the wrap-up of this presentation. So thank you very much. To summarize, that I wanted to say thank you, of course, all of you that has been following on site. And yeah, once again, thank you very much for the contribution and support on this pathway that we have built together. And thank you so much.
Thank you very much, Pablo. An applause for you. Any question for Pablo? If no question, right now we are 15 minutes behind the schedule, but I think we all, it's worth taking a pause of 15 minutes for a coffee break for both people on site and the ones probably online. You probably deserve it as well. So even if we are late, we wish you can be back at 11:15 for the next presentations. In this case, it will be the cluster of the fastest projects addressing also the challenges of the digitalization of battery testing. It's really worth continuing with us, so we really expect you can be present for the next presentation. See you back in 15 minutes then. See you at 11:15. Thank you very much.
Thank you, and enjoy the coffee break.
Hello, can you hear me?
Yes, we can.
Great, and you can see the presentations.
Yes. Yeah.
When I put it in full screen mode, I can't see the Zoom. So.
It's not in full screen now.
Oh, but if I do that, then
okay.
I can't see you. But is that still?
Yeah, we can read it.
That's good then.
Yeah, that's perfect.
Okay.
So welcome back. We really hope you enjoy your coffee break. We'll move ahead with our next block of presentations. As I was mentioning earlier, we will have our speakers of the cluster addressing the same challenge as Fastest Project, addressing this challenge of the digitalization of battery platforms. In this case, we have online connected Francesca Watson. She's the DigiBat project coordinator, but she's working for Sintef as a researcher. Francesca, I believe you hear us. The floor is yours.
Thank you very much. Yes. Hi, everybody. Thank you for that introduction. I am the project coordinator of DigiBat, working in Sintef, which is a research institute based in Norway. And this project was funded in the same call as Fastest, so we're all part of the TwinBat cluster, which means that the objectives are roughly the same overall. But when we were thinking about the DigiBat project, we decided to focus on removing some of the bottlenecks within testing, so using digitalization to remove some of the bottlenecks in battery testing. So this boiled down to this philosophy that we had, which was to standardize, automate, and accelerate the battery testing process. So what that means is, for standardization, we want to make sure that the data that we are collecting at different stages of the battery testing could be passed around and shared in an easy to understand standard format, which could be read by both humans and machines. Which would remove some of the bottlenecks to do with fragmented data and delays in processing data and understanding what data is as it's been given between different groups. Also, to increase the amount of automation that we can have in the testing process. So being able to automatically trigger the tests we need, whether they're virtual tests or physical tests, is something we wanted to focus on. And also accelerating the testing process in general. So if we can run faster tests or run fewer tests in a more targeted way, then that will speed things up and reduce costs and effort. So in essence, it boils down to wanting to extract more value from fewer tests. But one of the other things that we wanted to focus on in DigiBat was trying to make as much as possible open source so that we could share the results that we have and share the tools that we have to the wider community. Okay, so a little bit about the consortium and the project. We're a consortium of 8 partners. We're a good mix of research institutes, academic departments, and industry. And we have experts on ontology development, physics-based simulation, experimental cell testing and cell teardown, virtual testing, and also scaling up from cell level to system scale. Okay, so that was a bit about the background of the project. I should also say that we are a 3-year project and we will finish at the end of this year. So I wanted to just highlight one of the things that we've been working on. So this is not everything we've been doing, but one of the things we've been working on is the non-invasive parameterization workflow and automating this as much as possible. So the rest of the presentation will mainly be a description of this process. So when we're talking about creating a digital twin of a cell, we might have a, let me just see, might have a physical cell here represented by this part of the diagram. And then to create the digital twin of that, we need some data and some parameters, which can then be uploaded into a digital setup for further analysis. So in this most simple sense, we might want to do a little bit of testing and parameterization before we create our first edition of the digital twin. So in order to do that, this is a very simplified workflow. So if we take our physical cell here, we might run some tests on it, or run tests on several different of the types of cells of the same cell, run some cyclotests on it, run a simulation which has some parameters that are known and some that are unknown that we sort of make an educated guess at, and then update the simulation parameters until we are able to find the simulation parameters which give the closest match to the experimental results. And this is the sort of standard parameterization optimization loop. And then once we have these parameters, then we can use them in the digital twin. So this is a simplified way of saying that, but actually it's a little bit more complicated to do. So this is the slightly more complicated version, and this is the workflow that we've been working on. So we have the cell to be characterized down here. We run a few simulations so that we know what physical tests we want to do. We run some physical tests. We take the data from the physical tests and process it, and then we can put that back into our inverse modeling system and do the actual parameterization. So we take some information from the physical test, some information that we already know, and we run the optimization, and then we can update the parameter set with the optimal parameters which we get from matching the simulation to the experimental data. So I'm going to go through this in a little bit more detail now. So this is what we know to begin with. So we have a cell, we know what it looks like, we have some geometry information, we know the chemistry, and probably a few specifications. But one thing that we need to do in order to get the workflow to work is to have some standard data formats. And within Digibat, we've been doing this by looking at ontologies. So ontologies are just definitions of what things mean and the links between different terms. And there are already existing big projects with many partners looking at setting up ontologies for material science and things like that, and battery related things. But in Digibat, we've worked on developing these further and including ontologies for cell testing and ontologies for some of the geometries that we needed. So we've developed these ontologies and we fed them into the existing ontology workflows. And what this means as well is that once we have the ontology set up, we can take this general information that we know, and then we can write it in a standard form with standard definitions, which everyone should be able to understand. And not just everyone, it should also be readable by humans and by machines. So we can feed this information into machines as well. And part of the work we've been doing in Digibat, as well as developing the ontologies, is developing the tools that we need to create the ontologies and make these, to create the data models and set up these files in an easy way. So then we have our standard data, and we can take this first instance of the data, and code is the tool that we were using to write the data in the standard format, and we create an initial parameter set. And then the next thing we want to do is run some physical testing to get some actual experimental data. But we don't just want to run a full parametric sweep because that will take a lot of time and be quite costly. So we want to use some of the information we have and some forward simulation to find the optimal protocols that we need. So we can take the standard input format and we can put it into our simulation software. So we're running P2D simulation in this case using PyBAM, and we can look at the parameter sensitivities and we can run different cycloprotocols in the virtual test and see which one is going to give us the most information and is going to be the most useful for what we want to find out. And then we can output the cycloprotocol that is the optimal one. And we can do this relatively automatically just by setting up some scripts that we have. So this is this part of the diagram. So once we have this protocol, then we need to actually give it to the cycler and get it to run the tests. So of course, there is some human element to this because we have to set up the cycling test and we have to connect all the cells. But there is also a part of this that can be automated. So as I just described, we have the simulation output, which gives the optimal cycler protocol. And this we can have out from the simulation in a standard format that we can understand and we can convert to other formats. So we've developed another tool called BMGen within Digibat, which takes the JSON LD version of the protocol and then it translates it into different input files for different cycler systems. So we've been working on these three to start off with, and then we have a couple of others that we haven't quite got yet, but they're on the list of things to do. So what that means is that we reduce the human bottlenecks when we are converting the cycler protocol that we want to run to what we actually get in the input file. So we don't have to do that by hand, we can do that automatically. And it reduces the chance of error, and it also means that it's reasonably easy to run the same cycler protocol on different cyclers and the same protocol in the simulation. So that's that part. So then we set up the protocol automatically, we set up the tests with a bit of human intervention, and then we run the tests and we get out this raw data, which we can export as a CSV file. And the next big thing that we've been working on in Digibat is the data standardization from the cycler test. So this is actually part of the battery data format standard, which is a new open standard which has been released. And this is a bigger than Digibat. This has been work that's been done in collaboration with other organizations, international organizations, where we're trying to develop a standardized data format for battery cycling data. And this is open in the hope that other people will adopt it and more groups will start using this data format. This will make it easier for us to process data and share in the future. So once we have the cycling data in the data format, in the battery data format, we can then do a bit of processing on it. So the next tool that we've developed is this BDAT tool, which will take the cycling data and do some automatic segmentation and analysis. And from that, we can get the OCV curves, which we need for the parameterization step, which is the next part. So finally, we get onto the actual parameterization. So we take the OCV curves that we have from the data processing. We take the initial parameters that we got when we set up the cell in the first place, and we put them into our PyBop software, which is the software which will do the inverse modeling and the optimization. And it will do this by running forward simulations and then looking at the results and trying to match the output from the simulation with the output from the experiments. And we have this automatic optimization of the parameters. But this happens reasonably easily because we can read in these standardized data formats, standardized input parameters. We don't have to spend time writing all this stuff again. And that also cuts down the chance of any errors. So once we have the optimized parameters for that particular cell, then we can upload them to the initial JSON parameter set that we have. And then we have the parameterized digital twin. And of course, this isn't just something that we do once. We can do this many times. So we can keep updating. We can look for different parameters that we need or different test protocols that we might want to run. And this whole cycle will go again and again. So, like I said, that was just one of the things that we've been working on in Digibat. And the main thing that we wanted to do with the project was make sure that these, as much as possible, could be released as open source tools and adopted by the community. So then if we have this battery data format is the data format that we've been working on describing cycling data, and this is now available for people. And this is outside of Digibat. This is bigger than Digibat. It's part of an international effort to describe this data format. We have these three things here, which is not everything that we've done, but these are the three that I've just talked about, which you can find on the Digibat GitHub site. And then we're also working on the simulation software and the optimization for the cell modeling. So we have PyBum and PyBop, which come out of Oxford for optimization and simulation. And then we have Batmo as well, which is from Syntef. And these are all complementary and do slightly different things in different ways. But this is stuff we've been building on within the project. Yeah, so that was a very, very brief overview of one part of the things that we've been doing. We've also been looking at the other things, so scaling up to system level and parameterizing ECMs from field data and other things as well. But some of the main four things that have come out of the project are: one, the development of community standards; two, the open source tools that we hope will be of use to other people in the community; three, of course, is the faster digital twin development, the design of experiments, which I didn't really talk about here, and faster scale up between cell and system level. And then also the education part. So we have several early career researchers working in the project, and we have also had seminars and workshops. So, talking about that, the next thing that we will be doing is having a Digibat symposium in June. So I would like to put out a little bit of a plug for that. We're having several speakers from industry and from academia, from the project and from outside of the project. And we're also running a free BATMA workshop. So if anyone is interested, please have a look and consider joining us. Yeah, thank you very much for your attention.
Thank you very much, Francesca. Is there any question for Francesca, both on site or online? Since not, so thank you, Francesca, for being here today and to make a space for us. I know you are all very busy this time, so thank you very much. Let's move ahead with another online speaker. In this case, will be Justin Bouvet. I believe he's now connected. Yes. Thank you, Justin, for being with us today. He's the coordinator of the Thor project. He's also a researcher at the CA Research Center in France. So the floor is yours.
Okay, thank you very much. Let's just me check. Can you see the right screen for?
Yes, we can see your presentation. Yes.
Okay. So good morning, everyone. So actually, I'm not the coordinator of the Thor project. It's Liz Daniel, but she couldn't be here today, so I'm doing the presentation. I'm a work package leader in one of the work package. So I'm going to present the Thor project, which is about an innovative methodology for battery testing. So just about the context is that the battery physical tests are very expensive with a high environmental impact, and those tests can be numerous, long, destructive, complex, and sometimes we cannot do not enough tests, and they're also not enough representative of what the real battery will go through. So that's why the Thor project was implemented, and in this project, it started in June 2023. It's a four-year project, so we still have a full year ahead of us in the project. We are 9 partners coming from 6 different countries, and the scope is to innovate the battery design by developing a virtual tool that is able to reduce the number of physical tests for the development of the batteries. Like the main objectives of the project is to develop a 3 high-fidelity physics-based model to simulate the performance, the aging, and the safety behavior of a battery at the scale, module, and pack levels. And with those 3 physics-based models, they will be used to generate synthetic data that will be later integrated into a digital twin associated with a graphical user interface that will provide a very quick and accurate data for the battery behavior. And this will be based on the reduced order model, generated using the synthetic data generated by the high fidelity physics-based model. And there will be also an associated methodology that will be provided, and this will help to democratize the virtual testing for the battery development. It will be also useful to have a shorter time to market for the final product, and this product will be associated with a cost reduction of at least 20 to 30%. And the aim is to improve the battery design for longer lifetime and also better reliability and safety of the batteries. So as I said, we are a 4-year project. 1 year is still remaining. So what we have focused on in this 3 first year is the development of the high fidelity physics-based model. So that's where we are at the moment. And now, like in the project, all the energy is on the generating the synthetic data and also the digital twin development. Just a broad view of the work plan for the project. So at the beginning of the project, we have there are some cell module and packs that were specified and that are used for the different activities. So those cell module and packs are first used to develop the model for the performance, aging, and safety. These models are then used to generate the synthetic data for the development of the digital twin. And lastly, at the end, we will perform some tests on the cell module and packs and validate the final digital twin with those cell module and packs. So there are 3 models, so I will go quickly through the different models. For the performance modeling, the goal is to have a good prediction of the performance of the cell module and packs, and we want also to minimize the physical experiments that are needed to parameterize the model. So what we have been able to reach with the model with these activities to reduce by 50% the testing time for the model parameterization. And we have developed a new methodology that includes tests performed in single layer put cells. And also all this test reduction was achieved by performing a sensitivity analysis on the models that were developed, which helped us focus on the most important parameters in terms of their contribution to the final results of the models. And we also know where these different parameters affect the most the battery cycling. So is it at the low SOX, middle part of the state of charge, or at the end of the charge? With that, as I said, the sensitivity analysis helped us focus on a few different parameters. So we did some experimental characterization to measure these parameters that were then integrated into the P2D models, and those models were validated with a very good precision, as I will show a bit later. Just quickly into a bit more details about the characterization method. So we mainly use quite quick characterization methods that are based on impedance spectroscopy, performed on symmetrical cells at different temperatures. This data is treated using an analytical tool based on a linearized Newman model to obtain the kinetics and diffusive parameters. So with just this test, we are able to get the Arrhenius laws for the exchange current density, the liquid diffusion, and the solid diffusion. So with that test, we can pretty much characterize all these kinetics and diffusive parameters for a single electrode. So it's quite rapid. So these results were used to parameterize the model. So here is just a slide that is a bit packed, but it's just to say that there are a lot of parameters that are needed to parameterize the different models. And lastly, after this parameterization, we also need to do some validation experiments. So we did some charge and discharge tests at different temperatures, different regimes, and with that we get the charging the curves for the capacity, the potential, and also the temperature of the cells. And we have done that for single cells that were instrumented with thermocouples, and also for full packs modules where every single cells was instrumented, and so we can later simulate those behavior. In terms of where we are at in terms of the modeling, so the performance model was validated at 2 different scales. For the laboratory in single layer put scale, which help us focus on the electrochemical aspects, not taking into account the thermal aspects, and also into the 21700 full scale, which include the thermal aspect. And we see for these 2 levels of the models that were parameterized using exactly the same electrochemical input parameters, we have very good predictions of potential, the capacity, and also the temperature. So now that remains to be done is to do the same thing for module and packs. Then second part of the modeling activities are modeling of the aging that's led by VUB. And so the goal is to predict the battery lifetime considering the mechanisms present into NMC graphite cells. So these are physics-based model, high-fidelity models that are developed, and they take into account the lithium plating and ACI ACI growth as the main degradation modes. So here is just to say that is just to show like the comparison between the experimental and the simulation results. So the full lines are the experimental, the dashed are the simulations. It's just to say that the tool that is the model that is developed is able to catch very well the aging of the cells, at least at the beginning of the aging, with a very good precision. It's a bit more complicated than we see it a bit more here on this slide. It's when there is the knee in the aging. This is not caught yet, but this is in progress. And at least for the beginning of the first the beginning of beginning and to middle of life of the cell, we have a very good prediction of the tool. And also what is required now for this modeling activities is also to upscale the aging model at module and pack level, and by considering the different multi-cell configuration, the thermal management and the BMS, and also what this module and pack level model will be validated with driving and stationary profiles. And the third model is a safety model. So this safety model is developed by Ineris. And again, the goal is to predict the thermal runaway effects. So the energy release, the gas emissions, what are the ejectas during the thermal runaway at different levels. So first, what was done is to reduce the number of tests necessary for the model parameterization. And so in terms of achievement, like only 5 tests at cell level were needed, and 2 triggers were considered, like either overcharge and overheating of the cell. So we just need a few tests to parameterize the full model. So that's the idea between this methodology that is developed. And like different setups were also developed and used to have the most accurate thermal emission measurement possible at cell level, using in-house calorimeters developed at CEA and Ineris. And so in terms of a bit more details into this model, so the thermal runaway modeling is based on 3 Arrhenius laws to track the cell self-heating. It can take into account chemistry variation. So we did some tests were done using NMC graphite cells and also LFP graphite cells. Both cells were at the same format. And electrical phenomena such as overcharge or current flow have also been considered as a main contribution to the thermal runaway propagation inside the module. And this is just this has not been validated yet, but this is an idea of this is an idea of what this thermal model, like this safety model, can give you in terms of results. So you can detect when the thermal runaway happens. So as I said earlier, we still have 1 year remaining. And so now with these 3 three models. We once they are fully validated, we need to create some synthetic data for for the digital twin for doing the final digital twin. So as an expected outcome, so it will be done later, but the idea is to predict what is the best set of parameters for a given behavior. Sorry. So the digital twin will be there to refine the limits for better performance, longer and safer use. It will also be useful to fine-tune the battery design to tailor it to the application that is needed by the consumer. And it will be also a way to democratize the virtual testing. What we want to achieve is to have like a very good accuracy in the model, to have a very reliable and safe digital twin, and the time to market will be decreased thanks to the acceleration of the certification process linked with the acceptance of virtual tests as part of the certification process using this reliable digital twin. So that's about the Thor project. As I said, Liz is the project coordinator, so you have our coordinate here if you want to get in touch with her. But thank you for your time. If you have any question, I'd be happy to answer.
Thank you, Justin. And sorry for mistaking you. I thought you were the project coordinator, but
no, no problem.
Thank you very much, anyways, for taking the time to be with us today and present your results until now. We will follow up closely on your next developments. Thank you very much.
Thank you.
And now we will, well, applause for you.
Thanks.
We will now move again to on-site, because we were very lucky to be with Jasmine. She's on-site. She took the chance to be with us today, so thank you very much. Jasmine Nivalna, she's a project coordinator of Axelbat. I believe right now I get it right. She's also a project manager at AVL, and she will give us a nice presentation. So the floor is yours.
Thank you very much. Thank you for the nice introduction. So, I hope you can all see it's been in a good way, and also online, everything works perfect. So, as just mentioned, my name is Jasmine. I'm project coordinator of the Axelbat project, a funded project under Horizon Europe, focusing on the acceleration of battery development testing, because one of today's key challenges is, of course, that battery development is still too slow, too costly, and too test intensive, especially when automotive and safety standards must be ensured. So I will walk you through the overall project presentation, so the project results, the objectives, the consortium, the impact on the European competitiveness within the next 10 minutes.
Sorry to interrupt. We don't see the slides online. Okay, thank you.
And I would like to start with a short video as an introduction.
AxelBat, accelerated cell and battery testing. We're revolutionizing battery testing through digitalization, from single cells to entire systems. By integrating virtual models and live testing, we cut design time and cost, while boosting safety and reliability. Our hybrid V and V methodology uses smart simulations, real-time data, and process-optimized testing to validate future battery tech. Backed by the EU with almost €5 million funding and 11 partners across Europe, AxelBat is 80% complete and charging ahead. AxelBat, powering the digital revolution in battery development. Scan the QR codes and find out more on our dedicated website page, and follow us on LinkedIn.
So, as just mentioned, coming to the project overview. The project started on the 1st of April 2023 and is running until the end of this September, with nearly 5 million euros in total funding. It combines 11 partners, so different OEMs, battery manufacturers, as well as leading research institutes. Let's start with Austria. There we have the AVL, the coordinator. We do have University of Technology Graz, which is focusing on the process optimization. Then there's also Vata Storage, which are focusing on stationary use cases. Moving to Germany, there is Conviva, who are specialized in the linked data management platform, Fraunhofer, who are dealing with the electrochemical degradation, then University of Bayreuth, also dealing with the electrochemical degradation, and last but not least, Vato Innovation, who is a cell manufacturer. Let's now move to Italy. There's CRF, which are specialized in the industrial use cases. Then there is University of Florence, who are working on the thermal and mechanical models. Then moving now to France, there's Collège de France, who are cell testing and developing cells. I think I got all of them, yes. So, now coming to the objectives and results. As mentioned, the overall objective is to reduce battery development testing time by 30%. This is achieved by allowing testing activities to start earlier, optimization of battery development testing, and identification of critical time paths, a fully operational linked data management platform, and the application of digital twins in the framework of a hybrid validation verification plan. As you can see here, so the automotive use case is the Fiat 500. The stationary use case is the Vata War, which is next to it. Then we do have the model development, where we come now to the linked data management platform, and of course the process and method optimization. So, one of the sub-objectives to achieve the overall objective is the substantially improved cell, battery subsystem, and system measuring and modeling. So on the cell level, electrochemical models describing the degradation modeling have been achieved. So this has been done by the University of Bayreuth and Collège de France. On the battery component level, mechanical models supporting vibration and crash testing have also been developed. So this has been done by Gebauer and Grilla. And now coming to the scale-up methodology from battery to battery system via homogenization, this is still being deployed, and this will be conducted by University of Florence. Moving now to the second sub-objective to achieve the overall objective. So a system analysis which identifies failure modes has been developed. Then a newly developed method, so this is a really important point now, the confidence index, either in physical or digital testing, has been developed, and the integration is still in progress. So there has been a confidence index calculated, where we will also see the impact on the digitalization in Europe afterwards. And last but not least, the integration of the digital and physical tests in the hybrid and verification validation plan is still in progress. So the last objective, the last sub-objective is the advanced data provisioning within the battery verification plan. So as you can see here in gray, there is the normal battery development process. And in dark blue, there is the shortened battery development process. So on the first slide, or one of the first slides, we took as a state-of-the-art 24 months for the normal battery development process. I know this is really short because normally it's like 60, but we thought let's adjust to the Chinese battery development processes. So you can see here that we have a time reduction, although it's already only 24 months. So the time reduction is achieved via the linked data management platform, the execution of digital twins via the linked data, the execution of digital twins, and the process and method optimization, where we did identify the critical time paths. So, I'm already moving now to to my two last slides. So the impact of digitalized battery testing. I've split this into 5 points. So from a technological point, digitalization, of course, enables significantly time to market, which will strengthen our competitiveness. From the economic perspective, in terms of cost and competitiveness, so we will shorten the use of physical prototypes, which will lead to cost savings, of course, as time savings. Then industrial adoption. This is a really, let's say, critical point, because the barrier of using simulation models is still really high. So there the focus will be that simulation models have to be trustworthy, reliable, traceable in order to be fully available and integrated into decision making. And environmentally, as mentioned, using fewer physical tests will lead to CO2 reduction and also help to achieve the 2030 greenhouse gas emission reduction. And last point, the collaboration and interoperability is a shared ontology and metadata also across our, or maybe starting with our cluster, would help us to, let's say, set up a standardized regulation to be able to have a plan to develop traceable batteries and to ensure the direct use of results in the industry. Now really this last slide. So from digitalization to the industrial impact, first driver, as mentioned, is speed, so faster time to market, which will benefit into cost, quality and innovation. Then complementary, the combining physical and digital testing. Then the trust, as I mentioned, required would be that we have validated models, traceable and clear validation boundaries. So how is it possible to get a simulation model that is validated, traceable and reliable? And then moving to the interoperability, for now we do really have fragmented data structures, so the solution would be a battery ontology. And then scaling to industry, so the trust is needed again. And last but not least, the strategic impact. Europe can only lead in battery development if it's established a clear standard of and a certification for virtual testing. Good. Thank you very much.
Thank you, Jasmine. Any question? Everything today seems pretty clear, no questions. Let's move forward to the last presentation of this block. In this case, it will be our project coordinator who will be closing the loop. The project coordinator of FASTEST, Bruno Rodriguez, the floor is yours.
Hello again. I don't have any presentation, but in this case, it's just to bring up the topic of twin bed cluster. I will try to close the time that we have and to comply with the 12 o'clock to start our round table. But mainly I want to thank Francesca, Justin and Jasmine for accepting the invitation to be in our final event. But mainly what this shows us is that the twin bed cluster, it was, let's say, born 1.5 years ago. It was an interesting approach. Everyone was very keen on jumping on board, and since then we already attended some mutual events, some bigger events like the RTR 2026 and also the Battery Innovation Days on 2025, where we already show our progress and our results, and this will culminate with the white paper that I need to thank to Francesca to taking the lead in that point, and also in our side, Sushan, to also leading in the last couple of months this work internally. And it will be a very interesting approach because it will share our state-of-the-art development from the 4 projects, and it will also create, let's say, an open source approach of what was developed, and it will bring probably to the general public a different approach, not technical, but not so technical as we present in the normal results. And this was also a very interesting approach because it brings us together as 4 projects. I think in the beginning we were strangers, right now we are more or less known. I also attended, and I was forgetting, Digibat last year symposium. It was great. I also saw the other projects there. And I think if you can attend it, it is a good experience and you will learn a lot of interesting things there. But mainly, I would like to thank you, to thank the 3 other projects for this community, for this group. And even after Fastest comes to an end, I think the next challenge is to embed legacy and how we can keep this moving forward. So it won't die. In this case, I think with Digibet that it's the last project closing. So we will try to think in approaches. This is also happening in another cluster on how we can survive and we can endure further after our post-life project. And mainly it's to close with this and to thank you, thanks again to our 3 sister projects for this sharing and also for being here today with us for the final event. Thank you so much.
Thank you, Bruno, for your kind words. Right now, we are moving forward, in this case for the round table. So I'm inviting all the speakers to please join the stage. And I believe we have also online Marion. I don't know if you can hear us.
Yes, I can hear you.
Thank you. I don't know if it's possible to have Marion on the screen. Yes, so we can, please go ahead and take the stage. Most of the speakers you already saw, if you stay with us for the full morning. But in any case, please take a seat. I have the questions. Obviously, Bruno, you already saw him presenting the cluster collaboration. Jasmine was the Axelbat project coordinator. Marco Rodriguez is responsible for AI and data research at INEGI, and Suhen, doctor engineer at FedIO. Well, our idea today is to discuss further on what we saw. Today I will have some questions for you. Feel free to answer. There's no order. If you want to jump in, please, Marion, for you the same thing, even if you are online. If you want to jump in, please tell us and we'll be happy to hear you. I have a question for all of you, and whoever would like to be first, please jump in. It's in one sentence, what's the biggest competitiveness gain Europe gets from digitalization of the battery testing? We have several aspects, maybe, I don't know, speed, cost, safety, quality. Who would like to start?
I can start in here. In one word, I think in one word it's the speed up of the process. I think it's what characterized, and I think we saw in all the presentations that it was one of the key words. It's speed up the R&D process across Europe. And like Jasmine referred in her presentation, I think it's the only way for us to be competitive in today's world.
I think I can only support this speedness because, as I mentioned, speed is really, so with the speed everything other comes into place. So if we are faster, then we can all the other problems will get most of it rid of. So definitely speed. Oh, sorry.
Is this okay? Yeah, definitely. If I had to add only in one word, I would say also speed. As Jasmine mentioned, everything else will follow. I think that the point is not just digitalize per se, but to shorten or to use it as a tool to shorten the R&D cycle and the validation cycle, and to improve or accelerate the time to market. I would believe that for this to happen, of course, models need to be trusted, data need to be interoperable, and in the end, the ecosystem, the full ecosystem, needs to be trusted and integrated. That would be my take on this.
Seems like there is an agreement here. Let's see what Suhen thinks.
Exactly, I fully agree. I also see its speed. But more importantly, it's the speed results in the agility of changes that eventually having the connection between the virtual world and the physical world from the testing back to the development of the battery, and the speed results in the agility and for this changing world, I would say. Yeah.
Thank you. Marion, I don't know if you would like to add something, maybe something different apart from the speed.
Yeah, it's also about speed and cost, and I think we have all seen that these systems are highly complex, and we really need to reduce the set of possible configuration if we want to get this agility. And also for me is to pinpoint the most important configuration while keeping a rational basis also. So if we want to speed our decision. But I think this is what people are saying, so that we get more value from fewer tests.
Thank you. Interesting thoughts we hear. Maybe I'm putting you into a compromise, but this question is for you, Bruno. As a fastest project, you were mentioning before the importance of collaboration, cluster related, and in this case, as fastest coordinator, what would you say is the most important cross-project lesson that we could have learned or that you foresee in the future, like integrating tools, I don't know?
I think one of the approaches, and picking up also what Marion just said, it's to have a standardization approach in what we are going to do, because it will transform everything in the same language, let's put it like this. It will create a common approach to everyone that comes after us. It's a challenge. I think it's a challenge that we try to tackle in all of the projects, like we just saw with from Fastest to Digibat to Torrent to Axelbot. But if we can tackle this challenge, probably not in this project lifetime, but in the subsequent projects that will come, I think it will help to speed up, like we just said, R&D of battery testing. But it will also create that common approach for everyone, that we know we are not working in one language and then the other ones need to transform that in another thing. And I think that it's one of the approaches that we need to take. In our case, now going very specifically to Fastest, I think it is how we tackle all the different approaches from physical to digital testing, and how these can merge into a final result, taking advantage of the tools that we created, like DOE, LIMS, and also taking advantage to speed up the physical test and not spend time doing, let's say, redundant tests that we can do them digitally. I think it's more to merge things into quicker tools and faster tools. I don't know. The other ones want to add something?
Maybe related to this, at the end, everything is collaboration, and cluster takes away from one another. And maybe for the twin back clusters, Jasmine here, Marion online, maybe if the twin back cluster could agree on just one common thing to make these projects work better together and to obtain better outputs, but would you say it would be the one point that would help the industry putting this together?
So I would say definitely standardize, so a knowledge base, which would then lead to a battery ontology, because we are all working, like there's a lot of time and effort in every project. Of course, we have been working in the projects for the last, let's say, 4 years. approximately, more or less. And if we would combine all this work, or if we would work all on one knowledge base and have this information collected in one page, we could also easily transfer it then to the industry, because it's the same problem there. So every company works on their own structure, their own data, their own whatever, and it just takes a lot of time. And if we have one standardized data set, this would also help us further on to continue with the standardization, legislation, and then regulations, and so on and so on.
Yes, I think I agree a lot on this regarding the sharing of data and sharing on the different type of both benchmark and data format for the different aspects that we have been viewing today. And I think this is what is important if we want to move forward as a community on those aspects.
Great. I truly agree with what you're saying. It's always a challenge. At least in all the projects, I believe we are all involved, the standardization and the data sharing among all the project, inside the project, but also with the project clusters. I don't know if the other speakers would like to add something in this regard. If not, I have another question. In your presentation, Suchen, we saw that you summarized quite well what we've been seeing along today's presentations. You focus on the process and you told us that please keep this process in mind so you can later remember the importance of this LIMS final slide that you show us. So in terms of LIMS becoming real as a digitalization, what would you say, based on the presentation or based on your knowledge, are the three pieces of information that are most often missing in test data and then later break maybe modeling comparability and makes things complicated for you at some point?
Thanks a lot for the question. So actually, since you are asking for 3 bullet points, I will formulate my answer bullet point wise. So the first one is the description of the information itself. It's not the information pieces, it's the description of the information, in my opinion. So basically, during the cooperation, we often face this question, and everybody expects that all the information is standardized, is machine readable, which is not the case for most of the cases. And before that day is coming, I believe for us as project worker, we need to specify and define the information that we deliver to others. We have a lot of examples during the past months, during the integration. We have misunderstanding. What do you mean with this piece of information? Are you talking about milliseconds or seconds in a simulation? That happens all the time. So on one hand, we want to have a standardized structure for the battery testing, of course. We want to have one structure that every machine can read and every human can read. However, before that, we need to specify, if I give you this information, what's the unit of this information? What is the description of the information before you store that into the storage? In FASTS, we have this JSON scheme that defines, if I have a field of information, what is allowed for this piece, of course, right? However, at the same time, we leave some flexibility, namely, for each information, you can put your own description. Right? So we need both at this stage before we have a unified standardized structure. The second one is, normally we talk a lot about modeling, we talk a lot about sharing the model among each other. What do we do with the shared model? So there should be a configuration of the simulation of the model. That's some part I personally did not expect before working in fastest project, right? We have a lot of FMUs. How do I connect them? I have input A, B, C, D, E, F, output A, B, C, D, E, F. How can I connect them? If the definition is different, how can I make them work together and combine them into a simulation? That should be described in a file. We are all targeting the automated process. So again, it should be human readable and machine readable. So in Fastest, we have the JSON file to describe the simulation, how the simulation should be formulated. I would honestly say it's not sufficient, right? We only have several FMUs in the project. It's sufficient for now, but if we are thinking about improving the battery development in Europe, we should have a structure for the simulation files as well for configuration. If I receive a model from from other projects, how should I do with what should I do with it? So the last one is the failure. It's a project, so none of our components is perfect. So we face a lot of failures. The video you see is 5 minutes, but the test itself is 2 hours. So we debugging, we see failures of this and that component. Everyone makes a mistake. So the important part in this process, in my understanding, is that we define the failure mode, we make it traceable, and at each stage, if we have a failure, we need to be capable of going back to that component and find out what went wrong. In our project, we began working on that. Also, to be honest, at the very last stage of the project, because by integration, we noticed this problem, and we define the flag for each component. That's the reason you see it is running and it is complete. So sometimes it is running, it's not completing, right? So, and we check the log of each component, what has it delivered to the system to finish the test request. So I think this is the 3 most important information pieces. It's not information itself. Everybody has information. I believe this is how we use the information and how we exchange. That's the most important thing. Yeah, thanks.
Thank you very much. It was quite an answer. Thank you, thank you. I don't know if you would like to add something, although Sugen already, I believe he covered all. If
I may.
Yes, sure. Please go ahead.
If I may, just related to one of the topics that Shushan mentioned, which is regarding the information and semantics here is very important. From our side, during the project, we also felt those same barriers. According to my experience, I also feel that these kind of barriers, language and semantics barriers, somehow may be natural when we are breaking when we are breaking obstacles in such a recent or a novel topic or domain. But definitely this topic that Shushan mentioned, I think it's really important. And we as a project in the end and as a cluster, it's also interesting if we can take out of this something. Yeah. Thank you.
Indeed, indeed. This is important. I know both Sugen, for those who you don't know them, they have been working together quite a lot to overcome these challenges they are bringing up today. And one of the parts we were hearing out today was digital twin. And the importance of the digital twin, also the design of experiments we heard before, but in this case, digital twin. And as we have here an expert, as Marco, I would like to ask you some question, because sometimes digital twin, at least the concept, can be very broad, and it's difficult for people to narrow down what does it mean concretely. At least for you, maybe what would be your pragmatic definition of a digital twin, at least from your experience?
Indeed. Yeah, according to my experience, and I would say in the last decade, with the evolution of with a very fast evolution of hardware and software, digital twin eventually became this kind of buzzword or keyword among the industrial players. Eventually, everyone wanted a digital twin, right? But on a most pragmatic way, I would say that what's really important to take out of a digital twin, and I would frame it as a decision support layer, in this case for testing. The goal is testing, and we will use a platform or a system to support us in decision making, right? Here, and if we narrow down to what we are, to the domain that we are discussing here, the digital twin connects battery assets, data, models, test procedures, any artifact or resource that may eventually appear during the concept development. And the goal is that the digital twin give you a result in the end to support or to support the decision on what to test physically, what to test virtually, when and where and with which confident level. So I would say that in the end, the digital twin is not just a dashboard with a few data points, because this data means something. They have calculations behind, they have models running behind, they have algorithms. So in a nutshell, in a very pragmatic way, I would say that this would be a decision support layer. Of course, that you can include here inside any component that you want and you feel that will support you in reaching such objective. But as long as it's still connected to something physical, I would say, this is my approach to a digital twin. Thank you.
Thank you.
If I can give some words from a guy that didn't understand nothing about digital twins when this started, I already told that I learned yesterday in our final GA. I told that I learned a lot of words and things during these 2 years, from Kubernetes to MQTT brokers, everything. But I think the output that I can take from digital twin, and going with what Marcus said, is that it's the glue of several things that in the end gives you the output that you need to understand where you are going. It's like a guideline, but it's picking up the digital information that it's producing LIMS, that it's picking up the information that it's coming from the DOE. It's using also what is in the physical test bench, but in the end, it's not only a pretty thing that you look to the screen, it's much more behind that, because it's running a lot of things. And it's like, LIMS is the orchestrator of a lot of things, but together with LIMS, I think we have digital twin giving support for that to happen. And I think that's my main output as a guy that likes a lot of tech, but did not understand in the beginning, because like Mark said, it's the buzzword. Yeah, it was the buzzword about digital twin. We hear about digital twins everywhere, from processes to industry to even to automotive. And sometimes we only understand, okay, it's a nice interface, a nice dashboard, but it's a lot more. And I think this project shows this, and I think it was very, very, very nice to understand how this works.
If I may just add one sentence, I don't think digital twin only supports LIMS. So we govern different things. So digital twin is more govern the virtual processes and the models, and LIMS is govern the activities. So we're supporting each other, not only DT is supporting LIMS, I would say. Thanks.
Maybe one sentence to add, because I've also learned something within the project, of course, as I also have no real technical background. So in our case, it's not always a digital twin, but the digital twin is more common. So the use of the word digital twin. In the Axelbad project, it should be named digital master, because to reduce the time, there is no physical twin existing. So it's actually a digital master. But of course, we are all used to use the word digital twin, so we just mentioned digital twin, but actually it's a digital master.
Thank you. Great takeaways. I really hope you are enjoying this discussion. Thank you very much. I don't know, Marion, if you would like to add something. We don't forget that you are connected with us.
Maybe what I have also learned from Tor project and other project is that there is also a need in the industry to get a versatile and robust toolbox, because given the complexity of the systems that we are testing, there is not one single holistic solution. And what we have also learned is try to see how we can also work on modularity and interfaces. And this has also been addressed in the discussions, because depending on where the manufacturer wants to put the efforts, it will rely on different tools. And I think what is very difficult is how do we make this glue between different tools, so that the end users can choose the tools that are the best suitable to their questions, but still being able to aggregate what they need for the given questions. So we have also seen these difficulties on how to get this modularity of the different toolbox that we are developing, so that they then can be used and be exchanged between the different partners. But okay, this was to complete maybe a little.
Thank you very much. Interesting thoughts. I believe we are not always answering because we don't have all the answers. We are also raising questions, interesting questions, because this is research and we are still on the process of finding solutions. We see from the answers of all the speakers today that data sometimes is missing, also a common platform to integrate that data. So these are challenges maybe to be addressed commonly, hopefully in all the projects, but with other projects as well, also addressing the same challenges. Moving forward, we saw today as well the importance, obviously we still cannot skip some physical testing of the batteries, so sometimes we have to move forward to hybrid testing, let's say. So we combine this physical testing and this digitalization that we were speaking just recently. I have a question, an open question, whoever would like to answer, is like hybrid testing and digital twins, as we mentioned right now, are highlighted as industrial enablers. But what would you say is the strongest near-term use case? I don't know, reducing physical test campaigns, enabling early safety assessment, accelerating certification evidence, improving reliability predictions. I know you said before speed. Maybe you have now a different answer, because I know speed is important, but maybe you have different thoughts in this regard.
Yeah, jumping in, I would say that reducing the physical tests would be one very important aspect, because it's very close to a pain point. It's time consuming, it's costly, it's equipment intensive, so I would say that right there is a clear operational value proposition in my understanding.
Jumping in now, one thing and a challenge to European Commission is one topic that was raised, and I think it was for some OEMs, it's about certification, because right now you can do digital testing, but it will not be accepted because you still need to do the physical testing. So this is a little bit redundant, and probably since the reliability and the tests are showing the reliability of this, it can start to trigger some mechanisms to start to accept this as a certification to move forward, because I think that would push even further these type of solutions. Because right now, it feels like you are delivering the right tool, the right solution, but it will go against the wall because you cannot go further, and we'll have to go again okay, you will reduce the number of physical testings that you need to do, but you will still need to spend some time and some money doing physical tests. And I remember that someone raised this topic in RTR 2026, that is, certification also needs to move forward, probably and together with standardization. But this will be a challenge that it will need to be addressed soon, so we can also move forward with the digital twins, with all the digitalization of testing, so it can be taken seriously as a proof of that we are validating things in a real way.
You probably already know my answer because it's part of my project. So I would stick or underline Marco's comment as well. I would reduce the physical testing, because with reducing the physical testing, this will lead to such a time saving. But of course, all items you mentioned are important. So the combined, let's say, pool of it, in order to increase Europeans' competitiveness. So yeah, definitely all of them, but focusing on the physical testing.
Thanks. I believe my peers has already summarized perfectly for the industry and for the regulation. I want to speak out a little bit for the academic world. So bear me with being strict of the definition of digital twin. I'm thinking in the future not only the information flow from the physical to the virtual, right? So the strict definition of digital twin means that we have bidirectional information flow between physical and virtual. I'm thinking about the attractive use case would be that in the future, the battery and its digital twin, namely the modeling, can exchange the information. Like we are testing a model in the virtual world, and how can we improve the battery design in the physical world? That would be an interesting use case from the academic view. And don't forget the other digital twin pairs, that namely we have the physical testing and the virtual testing. The physical testing facilities can learn from the virtual testing processes, right? We automate a lot in the virtual world. We let our hands free. We only click on a button and the test is executed. Can that be easy in a physical test bench? Nowadays not, but I hope so. That's my thinking about the use cases. Thanks.
Thank you very much. So indeed, as a summary, you agree on different points, because at the end, reducing physical testing brings up reducing costs as well, so it's quite related, but also the validation of the virtual testing also helps out the physical testing with these synergies that you brought up, Suchen. So at the end, all comes to the certification validation of all these processes to smooth things up and be able to achieve this cost reduction, this time reduction as well, and the physical test bench moving towards a more virtualized and digitalized testing. I see that Marion is very shy and don't want to step in, but I have a question for you. Moving forward regarding trust, validation and certification, as we already saw that certification is sometimes a key point. Sometimes trust can be a bottleneck, and what would you say the most credible path to acceptance of virtual evidence in battery testing is? Standardized benchmarks, traceable data, third-party validation, regulator engagement. In a nutshell, what can projects realistically deliver in the short term regarding all these aspects?
Yes, I think for what we are talking about, combining virtual and physical test and going to regulations, trust is going to be really the bottlenecks for the acceptance of those virtual tests along real ones. And in fact, trust is also related to predictive capability. And here, with the different models that we are developing, we see that a clear identifications of what virtual tests can bring and what they cannot bring is very important. And we all have in mind that as a community, that the systems that we are studying are very complex multi-physics systems with multi-scarce aspects, from materials to the module, and with multiple load. We have the thermal, we have the electrical, we have the mechanical, with consequences on aging and safety. And for us to understand what virtual test can do and cannot do is going to be crucial if we want the people to accept it, and if we how to say this, if we say that the models that we're developing do everything and this is not the truth, we are going to lose the trust. And trust, I think, is very important. So to go to this, and trust, for me, trust is something that we build step by step by showing what we can do, what we cannot do, and where we need to improve. And in this path for the acceptance, I think that I do believe in benchmark, and I do believe in benchmarks that are built step by step with separated effects and coupled effects, and so that we can measure how we move forward in these predictive capabilities as a community. So yes, I would say I do believe in those simulation benchmarks. And maybe you were talking about with the different projects that are running, what we could do is on every project, I mean, there is a lot of people which are mastering the physics of what they're saying, and I think they could propose 2 or 3 benchmarks that they identify as the most critical with the physics that they have been working on, and so that then they're shared to the community with the related data and which type of trust they help build with these physical aspects on the different physics that we are facing. But this is one idea. I'm interested by other ideas of the different projects.
Thank you. I truly believe that obviously trust is important all along the process, but at the end we are working on the research and our will is to advance forward for these technologies to be further adopted from the industry especially. And for this adoption, I have a question for you, Jasmine, regarding this adoption and industrial competitiveness from your experience and the Axelbad perspective. What would you say is the industrial pain point that digitalized testing could solve first for this to be adopted faster at some point, and what would be the barriers for this adoption? The skills of the people working, the tools that we already mentioned, because there are different tools in the market, integration, data that was also raised.
Maybe the key barrier, let's put this first, is definitely the trust in the simulation models, because what is now stopping the use of simulation models instead of physical simulations is definitely the trust. So because simulation models are not yet traceable, not yet validated, not assessed. So, and what the other part is, so what would definitely help to overcome this barrier is a standardization and legislation again. But what would also help is that we are working on a confidence index, which is kind of an algorithm that is calculated and which combines different, let's say, metadata standardized sets, which is helping us already to define why these simulation models can be accepted and traceable and reliable. If this makes sense for you.
Yeah, indeed makes sense, at least for me. Any other remark from the cross panelists that you would like to say? Again, we heard standardization as a key point for all the aspect that we are dealing with in the project clusters with related data, tools, and so on. But for the rest of the panelists, I have more questions. I don't know who would like to answer. This is an open question. Feel free to raise your hand. How can we avoid great demonstrations staying stuck at project level? You spoke before, Bruno, the challenge of keeping this cluster collaboration after the project ends, but this also applies to the rest of the research of the project partners and the cluster partners in other projects.
I think the legacy is always a problem, mainly when we are talking in project set and in TRL6, because we are not sure if the next wave of projects will be approved and if we have a follow-up of our idea. So mainly this relies, and in an important topic that we also saw today, in the exploitation and project for the exploitation in the future. That is to understand where we can pick up, and even with the synergies that we created as a consortium, because we will probably exploit what we developed in the near future, coming together with joint agreements to share technology. But it would be interesting, and this is going for a wider view, to come together as a cluster, because if you merge the 4 projects, we will come to the perfect digital twin that we can have. We talked about trust, and if we merge all the reproducibility and the traceability that some of the projects proved regarding simulation data, it can show you that together we can have the perfect example. And one topic that it's always difficult, and now going again to the exploitable results, is it's difficult to share across the cluster the exploitable results due to IP, to a lot of other questions, trade secrets. But it would be interesting if there was some mechanism that can bring us together and try to identify, because sometimes the cluster help us understand, and you saw today what the other projects of the cluster were developing. These help us understand what is being done aside from fastest. If this didn't exist, we would be closed in our bubble, and we would think that fastest was the best solution in the world. But probably this could trigger some agreements for the future. But it would be interesting to develop the cluster, and this comes again with the legacy, also not to let the cluster die, and probably create these synergies for the future, not only for fastest in our internal key exploitable results and joint agreements, but also to try to create some synergies with partners from other projects, or even with other projects entirely, and to exchange information and ideas. This was one of the ideas, but it's always difficult in the end to bring it together. I don't know.
As we are 1 minute away from our time slot, just as closing remarks and related to what you just said, this continuation of cluster collaboration to try to to find a common pathway for these exploitation routes to be effective and validated and have a broader impact for the future. Maybe we can start with Marion online. If you would have to be concrete and just say a concrete action cluster that you would like to commit with in the next few months, what would it be? I don't know, a shared benchmark, ontology, metadata, platform, demonstrator, I don't know.
I think what would be interesting is that we had not foreseen to do it at the beginning of the project, is to test the battery data format and compare it to the battery data format that we are using internally into our project, and so that to measure the step to adhere to what is going on in the community. So I would recommend to go to this and test this battery data format that was presented by the people from the DigiBat project.
Any other point that you would like to add apart from what Marion just said? Otherwise, if we have to finish with one sentence, each one of you, what will it be if you can finish this sentence? For example, Europe will fit in battery testing digitalization if we, maybe Bruno, you can start.
I think I will use this last keyword that everyone uses. If we can trust in the results that are presented. I think that will prove that everything is working and we can move forward, because it will bring together certification, standardization, validation, exchange of data. So
I would say also if we established a standardized and regulation framework in order to support the virtual testing in part of the battery development.
Yeah, thank you. Well, I would say if we coordinate a shared European battery testing and validation infrastructure for hybrid testing, pushing for my side, of course. Sorry for that. Not just on individual R&D projects, but as a shared framework where assets and artifacts and resources can be made interoperable.
I would say if we start consider the battery testing data as information to be shared with others instead of consider the data as the company's property, then we are going to be faster.
That's a nice one. Marion, you are the last one.
Maybe just trust and confidence index that was suggested before.
So thank you all. I believe we have very interesting takeaways from today's conversation. Thank you for being available. Anyway, the responsible to summarize all these takeaways is Bruno. I really hope you have a good memory and and you can summarize what has been discussed today. But I wanted to thank you for your availability, good responses, and I think it was really interesting, the conversation among all of us. So Bruno, the remarks are on your side.
I will start with thanks to Mariana for the moderation and to guide us in this interesting conversation during the last 45 minutes. The main takeaway that I think we can take, or the main takeaways that we can take from this conversation, it's related with trust, regulation, and the speed up for that digitalization of testing can bring to the table, and to help us move forward in the competitiveness of the battery industry in Europe. I think it's the key points. We heard a lot, not only from the roundtable, but from the presentations today. I think we are moving forward related to simulation, to modeling, to the software side. The problem is and we felt that in our project, unfortunately, it's related with standardization. That it did not even prove to be a barrier because we could not reach there since we did not get an answer. But I think if we work together, and that's another topic that it's becoming more and more common. Alone, I think none of us can go faster or further in this battery development, and we see for what is happening in this community. But if we work together as a community and bring all the expertise that we can see, for example, here in this room and even on the partners online, I think we can move fastest in the battery development and bringing all these takeaways, and it can rely again and build trust in the results, the trust in the platforms. And all of that will also bring, and I understand also the other side from European Commission, it will also bring standardization, regulation, and it will, I don't know when, probably it would be good before 2030, but it will bring together in the end the digitalization of testing as a, let's say, a differentiating tool that we can have compared with the rest of the world, we hope. I think it's the only way that we can outtake our competitors in America or Asia. It's to be different in this aspect and not to be massive, but to provide the ideal solution to our partners in Europe regarding testing. This is my main takeaway for the roundtable. And do you want me to close also now the...
I don't know if there are further remarks from the people on the round table. No further remarks. Merci beaucoup, Marion. Thank you very much for being online, present with us in this discussion. And thank you all for, again, I'm being very repetitive, but thank you for the people connected online to follow up this conversation, and for these people on site as well for being today with us. From my side, just that, a big thank you also to our project officer that is present today, representing the European Commission, and follow up closely these presentations of today's final event. And again, I hope to see you soon and continue collaborating and being able to bring this impact in the future of the battery digitalization certification and obtaining reliable data and reliable platforms as well. Nothing else from my side. Thank you very much. I really hope you enjoy the journey of today, and see you soon.
Thank you.